Hello and welcome to this video for Chemistry 30 in the Thermochemistry unit. Today we're going to look at one form of Hess's law. The form of Hess's law that we're going to look at today is also known as additivity of heats. So there's a couple of different ways of applying Hess's law. This is the first one we'll look at today, and in the next video we'll look at the second way. So if I have a reaction that either proceeds in a single step or in multiple steps in a series of reactions, I can add those reactions together to get the delta H of the net or overall equation. So for example, if I have reaction 1, so I have a delta H for reaction 1, and then I have another reaction step, we call that delta H2, and then I have another reaction step, let's say, reaction 3. I can find the overall delta H of the net change that the three are going through by adding them together. Okay, so I can add my energy of reaction 1, my energy of reaction 2, and if there's a third or more, we can add them all together. But sometimes we have to manipulate our reactions. So that's what we're going to focus on. The reason we're doing this again is because sometimes reactions take too long, they're too expensive, the reactants are too rare, so Hess's law gets used. And there's actually a lab that we'll do to calculate the amount of energy released when magnesium burns, which is not easily measured. So the first thing you need to do is figure out what is the net reaction that I'm trying to get to. Okay, sometimes the question will give it to you, sometimes you have to write it yourself based on like predicting the products. Then you're going to manipulate those smaller given equations so that when you add them together, they cancel things that are on opposite sides, add things together that are on the same side, and you are left with the same net equation. Okay, so things that you can do to manipulate it. You can multiply or divide reactions by a whole number or a fraction. Whatever you do to the reaction, you do the same factor to the delta H. Or you can flip an equation. When you flip an equation, if it was endothermic, it becomes exothermic. If it was exothermic, it becomes endothermic. So you're going to change the sign. Then, like I said, you're going to cancel everything out and simplify, and you should end up with your net equation. If you do, then you can just add all the enthalpy changes to get the net enthalpy change. So this kind of makes the most sense by doing some examples, and we have several examples here. Now, this first example might look a little confusing because we don't usually see two things in brackets when we're looking at an element or a compound for that matter. But what this is saying is carbon solid in its diamond form, we want to convert it to carbon solid in its graphite form. So carbon solid can come in different forms, whether it's diamond or graphite, okay? Graphite is what you'll find in a pencil, and I'm sure you know what diamonds are. So how much energy change is required to make that happen? Now, these are the series of reactions that we're being given to use to get to that net reaction. So what I'm going to do is focus on each thing at a time. So I have 1 mole of carbon solid diamond in my net reaction that needs to be on the reactant side, okay? Now this reaction has carbon solid diamond on it, but on the oh, it is on the reactant side. Okay, so that is where we want it. We want it on the reactant side. So what I'm going to do is rewrite this down, and I'm keeping it the same. Okay, so carbon solid diamond plus O2 gas is making CO2 gas. I did not change that reaction, so my enthalpy also does not change, negative 395.4 kilojoules. Okay, so that's my first process, making sure the 1 mole of carbon solid diamond is on the reactant side. Now I need to find a reaction that has carbon solid graphite and make sure it matches the number of moles and the location. So this equation does have 1 mole of carbon solid graphite, but it's on the reactant side. I want it on the product side. So I'm going to flip that equation. Okay, the whole thing. So the products become the reactants. So my carbon dioxide is my now reactant, and my product is carbon solid graphite and O2 gas. My delta H also needs to be flipped to positive 393.5 kilojoules. Okay? Now, I've manipulated the 2 equations I was given. I need to add them together and see if I am actually, in fact, left with the net that I was looking for. So first of all, when they're on opposite sides, they cancel. So for example, I have 1 mole of oxygen on my reactant side and 1 mole of oxygen on the product side. So they both fully cancel with each other. Same with the carbon dioxides, reactant side and product side. So what I am indeed left with is carbon solid diamond as my only reactant and carbon solid graphite as my only product. And that matches the net reaction that we wanted. So that means I have done my manipulations correctly. Now I'm going to add my delta H's to get the net delta H of this net reaction. So negative 395.4 plus 393.5 gives us an answer of negative 1.9 kilojoules. Now sig digs, I'm adding here. So I'm only looking at decimal places. Those 2 numbers have 1 decimal place, so my answer needs 1 decimal place. And that is my final answer. I'm not looking at total digits. I'm just looking at decimal places when you're adding and subtracting. Let's look at another example. Just popping up my notes there. Okay, find the heat of reaction for hydrogen peroxide becoming liquid water and a half O2 gas. Now, when I have reactions that have multiple compounds and elements, I'm going to focus on the compounds and kind of ignore the elements because it'll usually work itself out from the other reactions. Okay? So what that means is I want 1 mole of hydrogen peroxide on the reactant side. This has my 1 mole of hydrogen peroxide, but on the product side. So I need to flip that reaction. So that becomes H2O2 liquid, producing H2 gas and O2 gas. And the delta H is now positive 187.8 kilojoules. Okay? Next, I need 1 mole of water on the product side. This has 1 mole of water on the product side, so I'm going to keep it the same. And again, just copy it down below. This is me showing my work. So I have H2 gas plus 1/2 O2 gas makes H2O liquid. Okay, the delta H is the same because I did not manipulate that reaction. So I have my compounds where they need to be. Like I said, there still needs to be this half oxygen on the product side, but let's cancel these and find the net reaction when I add these together and see if that works out. So my hydrogens will obviously cancel. There's 1 mole on each side. But there's a half on the reactant side and a whole 1 on the product side. Now, when we're dealing with fractions, when they're on opposite sides, you're going to subtract them. So to subtract them, I need to have them over common denominators. So if this is 1/2, then my whole 1 is 2/2. Okay? And the bigger one is going to cancel. This one, 2/2, is going to subtract the 1/2. And you are left with 1/2 on the product side. Okay, that's one way of looking at it. Or again, you can think of it as this half cancels with one of the halves here, leaving us with the other half. Okay, So left over is H2O2 liquid, my only reactant, and my products are H2O liquid, and now 1/2 oxygen is left because it canceled with the other half on the reactant side. And that is, again, my net equation. So see how the elements kind of just worked itself out. I didn't need to add a reaction to figure that one or to place that one. Now again, I add my delta H's. So we have 187.8 plus negative 285.8. I get negative 98. And again, I need a decimal place to match the decimal places of the other two numbers I added. And I get negative 98.0. Okay? Next example. Now in this example, the problem is I only have one compound. And the reaction for that one compound isn't going to give me carbon or hydrogen. So now I do have to focus on the elements and get the elements where they need to be. Okay? So my first reaction is the only one that has carbon in it. It has 1 mole of carbon, just like my net reaction needs on the reactant side. So I'm going to keep that reaction the same. So what I have is my carbon solid plus my O2 gas making carbon dioxide. I didn't do anything to this equation, so my delta H also stays the same. Next, I need 2 moles of hydrogen gas on the reactant side. This equation has hydrogen gas on the reactant side, but only 1 mole. So I'm going to multiply this reaction by 2 and also multiply the delta H by 2. So this leaves me with 2 H2 gas plus 2 times 1/2 is going to give us a whole oxygen gas, and we are producing liquid water in that process. So 2 moles of liquid water, because I'm doubling everything there. So my delta H is now double. Negative 285.8 times 2 is negative 571.6 kilojoules. Okay? And then my last reaction, I need 1 mole of methane on the product side. I have my methane here, 1 mole, but on the reactant side, so I'm going to flip that reaction. Okay? So my CO2 becomes a reactant, my H2O liquid becomes a reactant, and I'm producing CH4 and 2 O2s. The delta H is now flipped as positive 890.5 kilojoules. Now let's look at what we have after I've manipulated those three. Do they cancel and simplify to give me the net reaction? So my CO2s cancel. There's supposed to be 2 waters here. My 2 waters cancel. And my oxygens, I have 1 here plus another 1 here, so I have 2 in total on the reactant side and 2 on the product side. So they all cancel. So we are left on the reactant side with carbon solid and 2 H2 gas, and we are producing CH4. And that again matches our net reaction at the top. So now I add these reactions together. This time we're adding 3 together. You can add as many together as you need to get to your net equation. But keep in mind, sometimes they'll give you multiple reactions and you don't have to use all of them. You only have to use the ones that will help you get to your net reaction. Okay? So the answer for this is negative 74.6 kilojoules. Now let's look at this sample diploma question that I have here. That is something like I just mentioned where you don't have to use all equations. So the question usually will have instructions and say, use the following necessary reactions. Okay, which means you don't have to use them all. So like I said, when I have a reaction that has multiple compounds, I'm just going to focus on the compounds. Find the reactions that have those compounds and see if those reactions are, so I only have 2 compounds, so I'm only going to start using 2 reactions. This reaction has my CO, but I need to flip it so that my CO can be a reactant, making carbon solid and 1/2 O2, and my delta H becomes positive 110.5. So my CO is where it needs to be. Next, I'm going to look for my methanol. This has my methanol, 1 mole, where it needs to be, so I can keep that one the same. So carbon solid plus 1/2 O2 gas plus 2H2 gas is producing CH3OH, and that should actually be a liquid. My delta H stays the same since I did not manipulate that equation. Now, let's put these together and see if it gives us our net without needing to use the first equation given. So my half O2s can cancel, my carbons can cancel, and notice what we're left with. We're left with CO gas plus 2H2, making methanol. So I did not, in fact, need to use the first equation, okay? I only needed to use those 2 equations, and the hydrogen ended up there by itself from the methanol equation, okay? Now, sometimes I've had students ask me, can you do more than 1 manipulation to an equation? And yes, you can. You can flip and multiply or divide. Remember, you can also divide. None of these examples had that, but you can also divide. So 1010.5 plus negative 239.2 gives us an answer of negative 128.7 kilojoules, and that would be answer B. Okay, so this was Hess's law, additivity of reactions. Thank you for watching this video.